All right, welcome to the session, everybody. The core container revisited part of this is really a bit of a revealing the focus. We're going to look at Spring Framework 5.2 from a very specific perspective, core mechanisms that we had to revisit, core abstractions that we had to revisit in the 5.2 timeframe, with a strong motivation from high up the stack, from certain usage models, from Spring Boot, from Spring Data in particular in this particular release. So there was quite a bit of requirements coming down from other portfolio projects down to the core framework, to the core container, and I'm going to take this opportunity to reveal some of our of the changes that we made, the motivation behind them. Since there's quite a bit that has been introduced in 5.1 as well, and I suppose most of you are very aware of what 5.0 did, but not as aware of what came in 5.1. I'm also, for the initial part of this presentation, for the first part, I'm going to take the opportunity to discuss a few key design changes, design elements that we introduced in 5.1 first, and we're going into very 5.2 specific mechanisms right afterwards. So this is, of course, very close to my everyday work, since I'm in charge of managing the Spring Framework project. Quite a bit of the work that we did here is literally happening as we speak in my hands and in my team. So this is very hot from the oven. Be aware that this is work in progress. 5.2 is approaching a third milestone. It's not in the release candidate phase yet. Most of the features that we're discussing here are already available, either in 5.1 or in 5.2 M2. Some of them, and I'm going to point them out, I hope I don't forget, I'm going to point them out, are only coming in M3 or in RC1, so are not actually released yet. So let's go down to the core APIs, and as you are certainly aware, Spring Framework 5.0 came as an opportunity for us. The Java 8 baseline allowed us to literally revisit the entire code base, in particular the entire API surface. The language elements, the design capabilities of the Java 8 language elements are really shining through here. And we were able to revisit a lot of the API surface from the perspective of Java 8 streams, of course, from the perspective of using lambdas and functional interfaces. There's a lot of impact that it had, and it keeps having an impact. Refining Java 8 API design is kind of it's ongoing work that is still with us. There are refinements coming in 5.2, still along that theme. But let's just pick up a few central elements from that story. The first time that we were ever able to use Java 8 API types in our own APIs and SPIs was Spring Framework 5.0, but we only did an initial pass through the code base. A lot of follow-up came in 5.1, and it manifests in many ways. It's in particular the use of Java 8 API types as well, not just language elements. So it's about, for example, the new time types, local date time, and so forth. It's about the use of completable future introduced in Java 8. There's some more efficient reflection lookups we can do with the use of executable, a new base class of constructor method introduced in Java 8. There's quite a few things that, of course, the Java util streams that we introduced on that opportunity. The other part that we did, and this is also still very much with us, we're still refining the interfaces for the use of default methods. So if you've already closely integrated with some of the interfaces in Spring Framework 5.0 and 5.1, you might have noticed that default methods keep appearing. We are redeclaring, in particular, existing methods as default methods, so that you as an implementer of that interface, or some integrators as implementers of the interface, are having an easier time. This is in particular relevant for the callback interfaces. So if you customize, say, beam post-processing, or handler method interceptors in Spring MVC, then those are easier to implement now since the methods are all default methods and you just choose to implement the one you really care about. So that this all comes as a consequence of the Java 8 baseline. Another related effort that we went through is the nullability story. And I've been referring to it this morning mostly as a follow-up. There's a follow-up effort, a collaboration with Google and JetBrains for a better defined, a well-defined and properly released meta-annotation model behind this. But in essence, the story is very immediate in our API design. The entire API surface comes with clean nullability declarations. It's basically a form of null-safe API design. We declare our packages to be non-null by default. Exceptions to the rule, meaning arguments that can be nullable, return values that can be null, are explicitly annotated as such. So if you look at even just the Java doc or the API in the IDE, if you're calling, say, bean factory get bean, you've got a clear contract that the incoming parameters are usually not expected to be null, and more importantly, even that the return values are usually non-null, guaranteed to be non-null. You may rely on this. If they can be null, we annotate the method with nullable, meaning that the return value of that particular method can be null. This is a formal declaration that we're validating with some use of tooling. In IntelliJ IDEA, there's great support for this, both in live editing and also in terms of the inspections that you can run against the code base. We do that internally to make sure that our pretty large code base has clean nullability code paths so that all the assumptions that we make about something being null or non-null are actually valid down the entire call stack. You can do the same in your applications with our APIs being shipped with those annotations. You may have code of yours, application code, calling into the Spring APIs, and you may use, for example, IntelliJ's tooling, IntelliJ IDEA's tooling, to validate your calls into our methods. The tooling is simply making use of these formal declarations that we ship through those nullable annotations. The effect on Kotlin is, of course, even stronger, because in Kotlin there's an element of non-null enforcement in the type system. You can declare a type reference as not null. And the Kotlin compiler is going to allow such an assignment only if the outcome of the call of the expression that you assign is cleanly not null. So if you call any API with unclear nullability, this thing may be null, the Kotlin compiler is going to reject the immediate assignment. Whereas if you're calling a Spring API method, which is cleanly declared to be non-null, the Kotlin compiler is going to happily allow the assignment. This is one of the reasons why we did this, not only for the Java tooling, which is nice, in particular for the interaction with the Kotlin compiler, which is really quite an important enabler in our Kotlin story. All right. And here's just a few examples and a little bit of new API shining through. A good example is our object provider, which is reasonably recent, 4.3 introduced. But as of 5.1, it's also available with a programmatic call on the application context on the bean factory, get bean provider, and the type that you're interested in will give you an object provider of that type of foo here. And the object provider has several methods. And just look at the nullability. Get if available, in terms of its semantics, says, give me the object if it's present in the context. If it's not, return null, right? The same for get if unique. If there's a unique object, just a single one matching the type, give it to me, otherwise return null. Those methods are, of course, declared as nullable. The return value is nullable. Some new methods that we introduced in, that was back in 5.0, being provided as 5.1, these methods have a bit of a play with that nullability, basically. They have a bit of a twist in them. Get if available, and here is a Java util function supplier returning a default value if it's not available, means that the return value is guaranteed to be non-null. Either it's an object from the context, or it's the object that the default supplier produces. And the default supplier is usually bound with a Java 8 lambda expression or with a Java 8 method reference. or even a little bit more functional, to say like, if it's available, here's a consumer to do something with the object if it's available. If it's not available, just skip the call. So we have a few API methods that really make sense if you compare their nullable handling, where they are explicitly designed to avoid null return values in their semantics. And nullable declarations make this very explicit, not hidden in the Java doc. It's right there in the signature if you take the annotations into account. 5.1 also allows us to do a little bit more with the object provider if you have it. By the way, object provider can be programmatically resolved with the getBeamProvider call, but as shown above, it can also be injected into your component. If you just say, instead of add autowired foo, add autowired object provider of foo, then you have this indirection handle in your hands. That's what we will inject into your component for more sophisticated, lazy resolution of the object when you need it. So it's not an immediate reference of foo, it's a handle to retrieve a foo, a particular instance of foo, if you need it. And aside from the methods we were just discussing, the availability and uniqueness methods, there's a few further ones in 5.1. In particular for multiple matching objects. So if there may be more than one such bean implementing the foo interface in your context, then you can iterate over those. You can build a Java util stream over those, both of them basically lazily resolving as far as possible. There's also an ordered stream with Spring add order semantics taken into account across the matching instances in the application context. So some pretty sophisticated retrieval interaction with the container that we're enabling this way. Some oldie but goodie before we move on. This goes really nicely with the register bean methods that were introduced in 5.0. So the retrieval side of it, the stuff shown here basically, the programmatic interaction, programmatic retrieval against the container goes really nicely with programmatic registration of the beans. It's actually independent. You can programmatically retrieve components that are declared through the add configuration classes. And you can, of course, do annotation-based injection of components that you register programmatically. It's all mixing and matching. But stylistically, it goes together very nicely. So this is just snippets of how you can programmatically register components in a functional style as of Spring Framework 5.0. So there's a little bit of use of newer APIs in there, registering a component of type foo. A bean definition for that component will be registered underneath the covers, and one for bar, and the bar one comes with an instance supplier that is building a new bar instance and calls back to the container to retrieve an instance of foo that is to be injected into it over here. The example below is a little bit more sophisticated because it registers the bar components with an instance supplier that doesn't inject foo itself. It makes use of the new getBeamProvider method in 5.1. You pass an object provider of foo into that bar constructor, and bar can lazily interact with the container to retrieve the actual foo instance. And beyond that, it additionally registers marks the underlying bean definition as lazy init. So if it's a singleton by default, even the bar instance itself will only be created as some other component retrieves a bar from the container. So this is an alternative to configuration classes in the end. Entirely programmatic, no reflection involved, no annotations involved, and going really nicely together with programmatic retrieval. So this is the Kotlin version of it. We're not going to go into it in much detail, but keep in mind, in Spring Framework 5, we keep shipping Kotlin extensions. They are actually seriously refined over 5.1 and 5.2 as well. There's in particular a nice little, almost DSL-like experience that you can get out of the combination of Kotlin language features and our Kotlin bean registration DSL. There's no special setup necessary, just choose to use Kotlin, use a Spring context 5.1 or 5.2 jar, and start using those methods. They are delivered as Kotlin extensions coming in the standard jars. The Kotlin compiler automatically picks them up and applies them to the Spring API types by convention so that you can have a very nice out-of-the-box experience. This code is basically doing almost the same as the code before. It's just different twists down there with the inline register bean calls for a more DSL-like experience, and up there with the inline instance supplier. There's a bit of a convenience that comes out of Kotlin because we can use dedicated Kotlin reflection APIs. Also something we've been recently introducing and enforcing, that there is there's as little repetition as technically possible. In Java, we have to ask for explicit bean types in some cases because we can't infer the return types of lambda expressions and method references, whereas in Kotlin, there's a dedicated reflection API with a reliable return type inferred, so you can have a really nice shortcut syntax, in this case for registering the bar component, where we don't have to say bar.class, and here's how to create it. The supplier itself, this little snippet of code that creates an instance of bar, reliably tells us that it will be a bar class after all. So that's just for a little bit of Kotlin in here. Let's move on to a particular 5.2 topic, performance tuning. We have several efforts that I would summarize under performance tuning. It's mostly about startup optimizations, but it's, as always, right, any form of performance improvements, you're never really done. We are trying to optimize according to the feedback that we get, according to our own understanding of the trade-offs that we make. This is a totally non-trivial effort. Are you optimizing for startup time? Are you optimizing for peak performance? There's often a trade-off you have to make. Are you optimizing for single-threaded execution or for highly concurrent execution? These things are not all achievable, right? We have to make a certain trade-off between those optimizations. For 5.2, our focus was primarily on startup performance, allow Spring-based applications to be designed in a way where they start up as quickly as possible, at the expense of some of the initial web requests coming in, possibly taking a little bit longer than before, but at least the system itself is present, accessible, monitorable a little bit earlier. There's several facets to it, and I'm taking the opportunity to discuss a few of them. One of them is annotation processing. In our efforts to optimize what we call merged annotations and merged annotation processing, we arrived in 5.2 at the decision to completely re-implement the underlying annotation handling. So 5.2 comes with basically a new implementation of annotation processing, rewritten from the ground up, but hidden behind the same APIs. So existing code using annotation utils or annotated element utils would still work fine with binary compatibility, but actually uses the new mechanism, the new facility under the covers. What we call merged annotations is Spring's particular way of allowing composed annotations. If you've ever wondered how we process these things, like a REST controller being an annotation called REST controller, but having an add controller annotation and an add response body annotation as a meta annotation on the annotation type, right? This composing of annotations through annotating the annotation, what we call meta annotations. This is what we're calling merged annotation processing, and doing this efficiently is quite non-trivial. So 5.2 is basically our way to revisit the arrangement, and an important part of it is allowing for expressing hints, for optimizing, shortcutting wherever possible. If there are no annotations to be found on a particular component type, we don't need to go searching through it. We don't even need to reflectively look at its methods if we know that no such annotations are to be found there anyway. Reflection can be expensive. It doesn't have to be. But reflective scanning of the signature of classes can be somewhat expensive, in particular on startup. So there's The merged annotations API is already in 5.2 M2. Coming up in M3 or the latest in RC1 is some form of an annotation presence registry. More importantly, an annotation absence registry, where basically if you know that certain classes of yours, certain component types, or even certain packages of yours, whatever it is, if you know that there is no such annotation to be found in there, you should be able to register a hint with the runtime system that we don't even need to bother looking at those types for those particular annotations. So in its simplest form, you would just say like, I know that on this particular class, only those annotation types are ever to be found. And by simply expressing this in a one-line programmatic call, the container would skip the entire search for any other annotation types on those classes. This can be the intent for it. This is not actually shipped into it. The intent for it is to allow you to express those hints wherever you get them from. You can programmatically register those before bootstrapping, but in particular, you could take some index information, if you happen to have any, and translate it onto this annotation registry before you bootstrap, or at a very early phase of bootstrapping. So if you happen to have, for example, a Gendex index that your build produces, where information about the annotation types on the components is actually in there, you could choose to parse that index on startup, extract annotation information, and apply it to Spring's annotation processing infrastructure. When you then bootstrap the Spring application context, it would make use of those immediate annotation hints instead of having to reflectively introspect all your classes. The details of how exactly you would express yourself here are still to be decided on. We want to allow integration with indexes. From a core framework perspective, we are not going to ship out-of-the-box integration with indexes, with particular index arrangements. It's more of an integration point with indexes that a particular application arrangement could make use of. So it's opening up a core mechanism for external metadata, for external information from an index to be fed into it before bootstrapping. Another interesting topic that I'd like to discuss for just a bit, picking up again on something I raised this morning, are GraalVM native images. This is, of course, very closely attached to this theme that I outlined before. Trading off startup time for peak performance, that is basically, and trading off a reduced memory consumption for peak performance. This is pretty much GraalVM's elevator pitch, or at least Substrate VM's elevator pitch, so the GraalVM native image mechanism. Keep in mind that this is experimental at all levels. Even the recent GA release of GraalVM, GraalVM 19 GA, does not actually ship the native image support in production-ready form. You have to do an extra installation step to even get it, and it's labeled as a kind of early adopter, a kind of developer preview mechanism at this point. So anything we do, of course, is just as experimental, but it's quite interesting. We did a little bit of revision last year already, where we're trying to avoid unnecessary reflection points within the code base, like SPI level instantiation of defaults. GraalVM is very capable of handling reflection if you instruct it with reflection configuration, with certain configuration rules of what it needs to do when it encounters certain reflection points, of which classes it needs to be capable of delivering reflection information for, reflection metadata for. But we are trying to minimize the amount of metadata it needs there through some internal little refactorings where we're trying to be Graal-friendly within the code base. At this point in 5.2, we went quite far with just prototyping our way through the combination of Spring Framework 5.2 on Graal, on Substrate VM, using native images. The amount of explicit configuration can still be a little challenging now, and there's only certain configurations of Graal and of Spring-based systems that really work. But rest assured here that there is no conflict between GraalVM assumptions, like a fundamental conflict between GraalVM assumptions and Spring programming model elements. There's just a little extra configuration needed to make the configuration work. And towards 5.3, we're trying to get towards some kind of out-of-the-box setup. The details have yet to be seen, but it's already been prototyped that this is totally possible, that we would create the corresponding Graal reflection configuration on deployment of a particular Spring application so that the GraalVM finds all the metadata necessary for your application components when creating the native image, and the native image then contains all the relevant class information so that the framework then in this native image, when deployed as a native image, as part of a native image, can use its usual reflection APIs to get the metadata needed at runtime. So there's a few rough edges, of course, still, as you would expect there to be. We compiled the current state of affairs into this GitHub link down there. It's a wiki page where the current state of our understanding of the latest Spring framework generation, the latest GraalVM releases, is going to be maintained. So there's currently a reflection of the state of the art as of this week. And we intend to update this wiki page whenever new information comes in, whenever new Graal releases go out in particular. We have a very direct line with the GraalVM team at Oracle, and there's some very immediate collaboration with them. A lot of our feedback already went into GraalVM recent releases, this long release candidate phase that it went through. And there's further feedback of ours that will make it into upcoming GraalVM releases soon. So by the time that the GraalVM team decides to declare its native image support as production ready, which I expect sometime next year, there might, or there will, in all likelihood, be corresponding guidance from our side in terms of what you need to do to deploy a Spring application, to enrich a Spring application with the appropriate metadata so that the native image tool, Graal's native image tool, can do the right thing out of the box. So some way to go there, and some back and forth between the GraalVM and Spring engineering groups here. But of course, a very, very attractive option. I maybe should have even started with why would you want to do this? Well, you're building a native image. Basically, a lot of VM infrastructure is totally cut short. A native image of a Spring-based application can bootstrap in a fraction of a second. It can use a fraction of the memory that a full JVM-based deployment, a traditional JVM-based deployment would use. So you would do this primarily for a very immediate startup, very short startup time, and you would do it for dramatically reduced memory consumption. Those would be the two reasons. In particular for short-lived processes, for cloud deployments with very dynamic starting and stopping of processes, this is of course a very attractive option as it materializes for production purposes. So stay tuned, something will be coming in that space. Some of the immediate revisions, whatever we do, make it into Spring Framework 5.1 and 5.2 already. So we're trying to ship anything we can, any refinements we do out of the box, but the production level story very much depends on further GraalVM releases and production readiness declared on GraalVM's side for the native image model. All right, so much for that. There's a few implications on the component model. So just to make this very clear, performance tuning is not totally transparent. There's only so much we can do within the framework to optimize performance for certain arrangements. There's some impact onto the way that you declare components. You can basically help the framework in doing a better job in terms of startup time through explicit registration of components, avoiding the class path scan, or including a components index file for that purpose. You can declare as many beans as possible as lazy init, so that parts of your applications that might not ever be needed in a short-lived startup for a particular purpose are not ever bootstrapped. So there's a lot of help you can do at your component level. There's some new options in 5.2. For example, on configuration classes, you can set proxy bean methods to false, which is basically saying there's no need to create a glib subclass. I'm not going to call from one addbean method to another addbean method. I'm not expecting the container to intercept those calls. I just declare a few innocent and independent addbean methods with no direct references between each other. This is a much simpler arrangement. No need to intercept anything, no need to create a glib subclass for us at runtime. In particular, for a larger set of classes, this may seriously impact the overhead of class definition on startup. And this is also something that made it into our own configuration classes for typical Spring Boot deployments in the Spring Framework 5.2 boot to the 2 arrangement. So we're also making some use of this ourselves. By the way, this is semantically the same as putting the addbean methods on just any non-configuration class. So this was totally possible before. We're calling this light configuration classes. So addbean methods on any other components without an add configuration stereotype on top would behave the same way. But in order for this to still be recognizable as a configuration element and to be found when you look for add configuration classes, we decided to introduce it as an option, as an attribute of configuration classes themselves as well. Along a similar line, you may choose to use interface-based proxies. If you design your components to be decorated through interfaces, like service interfaces, with no need for the framework to create a target class proxy, as it's called. This simply means that we don't need to create the glib subclasses on startup. We can use the JDK's own Java-Lang reflect proxy facility instead, as long as your proxies only expose interfaces. This is a mode of operation that the framework always had, always came with. And this becomes a little more important now. If you're trying to optimize for startup time, or if you're trying to design an application for deployment as a native image on GraalVM, you're much better off in avoiding glib subclasses. Make use of the standard JDK facilities instead, and you'll have a much smoother experience in those scenarios. So that's 3 examples for the kind of lines that we're working towards, trying to optimize annotation processes, considering index arrangements. There's the whole GraalVM native image topic. And there's also this shining through in the component model, an aspect of our work here. This is only going to continue, and some further work, I'm sure, will materialize in the 5.3 timeframe here. All right. Final section for today's purposes, for this presentation's purposes, is the reactive topic. Of course, Spring Framework 5.2 is an opportunity for us to kind of have a further iteration over our core reactive facilities. You are certainly aware that reactive has been a topic. We've been talking about it quite a bit. And this kind of reactive web controller is pretty much the model that we introduced in 5.0. So much shouldn't be much of a surprise. Just imagine that this is a web controller with 2 HTTP mappings, 2 HTTP endpoints, one of them for /users, returning this flux of users, saying here's basically a reactive stream of user elements that you can render out to the caller as a response whenever you're ready to do this. And the other one has an incoming path variable called some underlying repository with a mono of user return value, which is basically a set of instructions of how to arrive at this user element for the given ID whenever the processing stack is ready to render it out. So much for just the basic semantics. This is basically the 5.0 state of affairs. What we initially introduced is what we call WebFlux. This is a totally separate web stack, highly efficient web stack based on Reactor Netty and the Netty networking library underneath the covers, or adapted onto like Tomcat or Jetty or Undertow as a core container, as a core HTTP engine. The entire stack is non-blocking, of course, from top to bottom, so it doesn't share any of those semantics with the servlet API. In parallel to that, we have the Spring Web MVC stack, which is still running on servlet containers and in particular on servlet API assumptions. So within the servlet callback model where you receive a request, you own a thread, and during that thread, you process the request, you write a response, and then you return and release the thread back to the pool. So we have two parallel web stacks, one of them traditionally servlet-minded, one webflux-oriented, one reactively oriented. The twist here is that reactive signatures like these here, mapping methods, HTTP mapping methods, returning a reactive streams publisher, are actually supported to some degree on Spring MVC as well. On Webflux, you have to code all your endpoints, your entire code, with the reactive streams model. On Spring MVC, you may decide to declare some of those endpoints, the ones that really truly benefit from reactive processing with a reactive streams publisher. So if you deploy these kinds of endpoints to Spring MVC on the servlet stack, we would still try to do the best we can. We detect that you're using reactive streams publishers here. You're calling get users. We switch the servlet request as we get it from the server container to its async mode, and then we are adapting this async mode of servlet processing to reactive streams. So we're trying to bind your reactive stream, this flux, to the servlet async mode, and as the elements materialize, we're reawakening the servlet async request and writing those elements. So it's a callback model that the servlet container offers, a certain mode of processing that we can use in particular for response elements as reactive streams publishers. There are limitations to this, but we're really taking it very far. We're trying to make everything possible that is technically sensible, so you can even have a little bit of a reactive streams experience on Spring MVC on the servlet stack if you wanted to. Even more than this, there's a new reactive transaction management model in Spring Framework 5.2. This is intentionally a very similar example. Imagine that we are not coding a controller right now. We are building a service class, a little bit of an indirection, a service facade. This one is very simple initially. It just delegates to an underlying repository, and it adds a transaction boundary to it. It does so using the common edge transactional model. So by just taking methods like these here, marking them with add transactional and having add enable transaction management in your configuration, we would intercept them. A transaction interceptor comes in, tries to intercept those calls, but understanding in 5.2 now that these are returning reactive streams publishers, it doesn't try to naively intercept them and start a transaction, bind it to the thread, call the method, and then commit it and rolling it back. That doesn't make any sense with reactive streams publishers. These methods are not actually doing the underlying processing. These methods build a pipeline for how to arrive at the user objects. So there's no point in trying to do any kind of thread-bound transactions. So we immediately switch, looking at the return type, we immediately switch into the reactive transaction manager mode of operation. We are taking the reactive streams publisher coming out of that method. We are decorating it with a transactional operator. This is sort of a transactional decorator for the underlying pipeline. This operator puts transactional elements, basically transactional resources and handles, into the underlying reactor context. So it always is being turned into a reactor flux or mono. And we are trying to make use of a particular reactor feature, the reactor context, to store certain elements that go with the flow, basically, through the reactive pipeline. So a transactional operator just basically starts a transaction, or actually adds an operator that starts a transaction. Then this operator would store the underlying metadata in the reactor context, and at the very end of processing, it based on the error signal or regular outcome, a successful completion, it would trigger a rollback or a commit. So it does the right thing, semantically very intuitive, automatically, just with the standard add transactional element and with add enable transaction management being active. This needs a particular SPI implementation, so there's a new SPI called Reactive Transaction Manager. And this is an alternative to the good old platform transaction manager that Spring is traditionally using for thread-bound transaction, There are currently 2 implementations for R2DBC, our relational, reactive relational database connectivity project, and for MongoDB. Both of them live in Spring Data at the moment. This may be revisited at some point, but for the time being, both of those implementations live in Spring Data. So by choosing to use Spring Framework 5.2 and the Spring Data Moore release train, you can have the complete experience very quickly. There's also a programmatic arrangement. You may choose to programmatically interact with the transactional operator arrangement. So instead of doing an annotation-driven transaction, you may also programmatically compose a reactive streams publisher that you choose to decorate with such a transactional operator. There's a programmatic equivalent for it. All right, so much for reactive transactions. There's quite a bit of work in the Spring messaging module where we basically take the existing messaging arrangement with its message mapping annotation and all of the supporting infrastructure that comes with it. There is a reactive equivalent for that infrastructure now for a completely reactive streams-based message interaction model. This is primarily used with RSocket, as mentioned in the keynote this morning. So just to give you an idea, this is programming model-wise very similar, message mapping annotations within the common Spring component model, and then different flavors of how you would express yourself with an incoming payload, a simple payload coming in, and a reactive streams publisher for the response coming out of it, then built into the reactive stack at runtime. Totally non-blocking, highly efficient processing, and very close to the underlying metal in RSocket. Since RSocket itself is also reactive streams-based, this is a very immediate match. There's, of course, a way of returning a stream of elements, and there's also a channel mode of operation according to the RSocket model, where you can have a sequence of elements, basically an open-ended stream of elements coming in and an open-ended stream going out. And you can return a reactive streams publisher that just does whatever you want that channel to do in terms of processing those elements. So the part that we're doing at Spring Framework level is this immediate and very natural integration into the Spring messaging module, into the annotation-based endpoint model. For Spring messaging that is very similar to what you would use when you were using Stomp on WebSockets, for example. You're using the same programming model, a little specifically bound, of course, to the Stomp protocol, but it's fundamentally the same structure, the same configuration elements, and wherever possible, the same semantics and the same conversion infrastructure underneath the covers. So last but not least, there is also a plan for revisiting application events. The application event facility is a core part of the Spring application context arrangement, and is traditionally, well, it's simple in its semantics. There's a publish event mechanism where the container itself and some of the integration with the container, some of the integrated infrastructure can publish events. You may also publish events yourself, of course, programmatically through injecting the application context or its application event publisher part and calling publish event on it. There's standard events with an event hierarchy. There's what we call payload events, where it's sufficient to just pass in the payload for triggering an event. Behind the infrastructure, there's an SPI, a multicast infrastructure for how those events are going to be dispatched and how they are going to end up in what we call application listeners. The event listener annotation is basically an annotation-based form of such an application listener. Traditionally, this is just an incoming event, process it, void return value, and whatever happens, right? You're not really supposed to do some expensive work here. You could trigger some async steps manually from here if you wanted to. It's basically just a notification, a callback signal that that event happened. And in a standard setup, this code is actually going to execute within the caller's thread. So whoever does publish event, within that thread that calls publish event, all of the listeners would run. There are configuration options to have a thread pool behind this and so forth, but in a standard arrangement, that's pretty much what happens. So an idea for M3 or possibly RC1, still for the 5.2 time frame, is that we would allow those methods to not necessarily be void here, or declare a return event directly, but rather use reactive streams as well, like we do in other places. A mono void is basically just a completion signal saying, oh, this is actually building a reactive streams publisher. Dear multicaster, please integrate this particular publisher, this particular reactive streams pipeline into your pipeline processing. So the multicaster would get a new mode of operation, a new understanding of how to deal with reactive streams publishers that might come from several listeners. With one listener, it's trivial. It's more interesting if several listeners return reactive streams publishers, and it would then do the right thing, basically, to wrap them up efficiently with a reactor processor and execute them behind the scenes in an asynchronous fashion. So by just allowing these signatures with a completion signal or with an event to trigger when we are done processing my event, then the publisher would end up producing my other event that we would finally publish behind the scenes whenever it's ready. And there's also an idea of not just allowing to use Reactor for this, Reactor monotype, a real reactive streams publisher with back pressure support. Like we do in other places, we are also considering to support completable future as a return value. This is, of course, the Java util concurrent completable future from Java 8. You can do this in Spring MVC already. You can do this in the Spring messaging module already. So we figure we could also support it for the application event facility. So this is work in progress or design in progress to be implemented before 5.2 RC1 still. To add some spice to the application event facility and close a bit of a gap there. So the underlying infrastructure, since I just mentioned completable future adaption, actually uses an adapter model. In case you're wondering how we do this, it all ends up in Reactor. But if you return a non-Reactor type to us, or let's put it the other way around. If you return a Reactor mono or Flux to us, we immediately integrate this into our core reactive infrastructure directly. If you return something else to us, like an RX Java flowable or an RX Java single, or if you return a completable future to us, then we would try to adapt them to the corresponding Reactor types. For completable future, we would wrap it with a mono. For the RX Java flowable type, we would wrap it in a Flux. If you return a plain reactive streams publisher to us, we would also decorate it with a Reactor Flux accordingly to be able to fully integrate it with the underlying infrastructure. So this happens pretty much underneath the covers. It's what we call reactive API adapters. And just in case you're wondering, since we were talking about Kotlin coroutines this morning, this is also the way that we integrate coroutines. It's kind of a special reactive return type. The Kotlin flow type and the Kotlin deferred type are understood along the same lines. A suspend function, a suspend fun method in Kotlin, naturally returns those, basically, like a Kotlin flow. And underneath the covers, we automatically adapt it to a Reactor Flux and process it along the lines of a regular reactive streams publisher integrated with the entire reactive infrastructure that Spring comes with. All right, that's all I had for you today for this session. So we were talking about a few Java 8 API design topics. Annotation processing, huge deal. Hopefully you won't even notice. Just a little bit more efficient in processing your annotations, but a refactoring underneath the covers, but a pretty huge one. There's the reactive transaction management model for, in particular for R2DBC and MongoDB for backends that actually understand, have proper transaction semantics that we can attach while being reactive streams-based. There's RSocket messaging integration, which is the Spring messaging module coming with generic reactive messaging infrastructure and particular RSocket bindings coming with them. And just a little bit at the very end, we were referring back to Kotlin coroutines and the way that they are integrated with our underlying reactive API types. So that's how the big common themes connect to the storyline of this particular session today. So thanks for your attention. I'm of course happy to take any questions. Just come up to the stage. We can have any conversations about any of those topics. Otherwise, just pick me or anyone else from the engineering group as you find us in the hallways. So thanks for your attention. Enjoy the rest of the show.